Welcome. Today we're diving into the fascinating world of complex numbers. You might have heard about them in math class, but what exactly are they? Complex numbers extend our understanding of numbers beyond the real line, opening up a whole new dimension in mathematics. They're essential in fields like engineering, physics, and even art. In this video, we'll explore what complex numbers are, why they matter, and how they're used. So let's start by understanding the basics and see how these numbers can make the impossible possible. Complex number is a number that has two parts, a real part and an imaginary part. It's usually written in the form a plus by, where a is the real part and b is the imaginary part. The I stands for the imaginary unit, which is defined as the square root of -1. This might sound strange at first, but it allows us to solve equations that have no solutions in the real numbers. For example, the equation x2 plus 1 equals 0 has no real solution, but with complex numbers it becomes solvable. Let's talk about the imaginary unit represented by the letter I. By definition, I is the square root of -1. This means that I2 equals. It might seem a bit abstract, but this simple idea is the foundation of complex numbers. With I, we can express numbers that were previously impossible to write, and this opens up new possibilities in mathematics and science. Every complex number has two components, the real part and the imaginary part. For example, in the complex number 3 plus 4i, 3 is the real part and 4i is the imaginary part. These two parts work together to form a single complex number. You can think of them as coordinates on a plane, with the real part on the horizontal axis and the imaginary part on the vertical axis. Complex numbers can be visualized on a special graph called the complex plane. Here, the horizontal axis represents the real part, and the vertical axis represents the imaginary part. Each complex number corresponds to a unique point on this plane. This visual approach helps us understand how complex numbers behave and interact, making abstract concepts much more concrete. Adding complex numbers is straightforward. You simply add the real parts together and the imaginary parts together. For example, if you add 2 plus 3i and 1 plus 4i, you get 2 plus 1 plus 3i plus 4i, which equals 3 plus 7i. This process is similar to adding vectors, and it's easy to visualize on the complex plane. Subtraction works just like addition. To subtract one complex number from another, you subtract the real parts and the imaginary parts separately. For instance, 5 plus 6i minus 2 plus 3i gives you 5 2 plus 6i 3i, which is 3 plus 3i. This operation is also easy to represent visually, helping you see the movement on the complex plane. Multiplying complex numbers is a bit more involved but still manageable. To multiply a plus by c plus d, you use the distributive property. A plus by c plus d equals ac plus addi plus bci plus bdi2. Remember I2 equals, so you substitute that in and combine like terms. This gives you acb to add plus bci. Multiplication can also be visualized as rotating and scaling on the complex plane. Dividing complex numbers involves a special trick. To divide a plus by c plus d, you multiply both the numerator and denominator by the conjugate of the denominator, which is cd. This process eliminates the imaginary part from the denominator, making the division possible. After simplifying, you get a new complex number as the result. Complex conjugate of a number a plus by is a by. In other words, you change the sign of the imaginary part. Conjugates are useful for simplifying expressions and performing division. They also have interesting geometric interpretations on the complex plane as they reflect points across the real axis. The absolute value, or modulus, of a complex number measures its distance from the origin on the complex plane. For a number a plus by, the modulus is calculated as the square root of a 2 plus b2. This is similar to finding the length of the hypotenuse in a right triangle using the Pythagorean theorem. Complex numbers can also be written in polar form, which uses the modulus and an angle called the argument. The polar form is r cos theta plus I sin theta, where r is the modulus and theta is the angle with the positive real axis. This form is especially useful for multiplication and division, as it simplifies the calculations. Euler's formula is a beautiful connection between complex numbers and trigonometry. It states that e theta equals cos theta plus I sin theta. This formula allows us to express complex numbers in exponential form, making calculations even more elegant and powerful. It's a cornerstone of higher mathematics and engineering. Using Euler's formula, we can write complex numbers in exponential form, re theta. Here, r is the modulus and theta is the argument. This form is especially handy for raising complex numbers to powers or finding roots, as it turns multiplication into addition and division into subtraction of angles. When complex numbers are in polar or exponential form, multiplying them becomes much simpler. You multiply their moduli and add their angles. For example, if you have r1 e theta 1 and r2 e theta 2, their product is r1 r2 e I theta plus theta 2. This geometric interpretation makes complex multiplication intuitive and powerful. Similarly, dividing complex numbers in polar form is straightforward. You divide their moduli and subtract their angles. For example, r1 e theta 1, r2 e theta 2 equals r/r2 e I theta 1 theta 2. This approach simplifies many calculations, especially in engineering and physics. The imaginary unit I has a repeating pattern when raised to different powers. I1 is I2 is -1, I3 is I, and I4 is 1. After that, the cycle repeats. This property is useful for simplifying expressions involving powers of I, making calculations much easier. Finding roots of complex numbers is another fascinating topic. In polar or exponential form, taking the nth root involves taking the nth root of the modulus and dividing the angle by n. This process reveals multiple roots, evenly spaced around the complex plane, forming beautiful geometric patterns. Complex numbers allow us to solve quadratic equations that have no real solutions. For example, x2 plus 4 equals 0 has solutions equals 2i and x equals minus 2i. This expands our ability to solve equations and understand mathematical relationships that were previously out of reach. Complex numbers are vital in engineering, especially in electrical engineering. They're used to analyze alternating current circuits where voltages and currents are represented as complex numbers. This approach simplifies calculations and helps engineers design efficient systems. In physics, complex numbers are used to describe waves, quantum mechanics, and many other phenomena. For example, wave functions in quantum mechanics are often complex-valued, allowing for a richer description of physical systems and their behaviors. Believe it or not, complex numbers also play a role in art, particularly in the creation of fractals. The famous Mandelbrot set, for example, is generated using complex numbers. These mathematical patterns create stunning visuals and have inspired artists and mathematicians alike. The concept of complex numbers dates back to the 16th century, when mathematicians encountered equations with no real solutions. Over time, the idea of imaginary numbers was developed and eventually accepted as a legitimate part of mathematics. Today, complex numbers are a fundamental tool in many scientific fields. Several mathematicians contributed to the development of complex numbers, including Raphael Bamelli, Carl Friedrich Gauss, and Leonhard Euler. Their work laid the foundation for modern mathematics and opened the door to countless discoveries in science and engineering. Let's take a closer look at the complex plane. This two-dimensional space allows us to represent every complex number as a point. The horizontal axis is the real axis, and the vertical axis is the imaginary axis. This visualization makes it easier to understand operations like addition, subtraction, and multiplication. Complex numbers can be interpreted geometrically as vectors from the origin to a point on the complex plane. This perspective helps us understand their magnitude and direction and makes operations like addition and multiplication more intuitive. In signal processing, complex numbers are used to analyze and manipulate signals. They allow engineers to represent signals in terms of amplitude and phase, making it easier to filter, compress, and transmit information efficiently. Control systems often use complex numbers to analyze system stability and response. By representing system behaviors as points in the complex plane, engineers can predict how systems will react to different inputs and design better controllers. In fluid dynamics, complex numbers help model the flow of liquids and gases. They simplify the equations governing fluid motion, making it possible to solve problems that would otherwise be extremely difficult. Computer graphics often use complex numbers to perform transformations and create stunning visual effects. For example, rotating an object in 2 dimensions can be done using complex multiplication, making animations smooth and efficient. Robotics engineers use complex numbers to describe the movement and orientation of robots. This mathematical tool helps them program robots to move accurately and perform complex tasks in real-world environments. In acoustics, complex numbers are used to analyze sound waves and vibrations. They make it easier to study how sound travels, interacts with materials, and creates different auditory experiences. Economists sometimes use complex numbers to model cyclical behaviors in markets and economies. This approach helps them understand patterns and predict future trends, providing valuable insights for decision-making. In biology, complex numbers can be used to model oscillatory processes such as heartbeats or neural activity. This mathematical framework helps researchers analyze rhythms and patterns in living organisms. Cryptography, the science of secure communication, sometimes uses complex numbers in advanced encryption algorithms. These mathematical tools help protect sensitive information and ensure privacy in the digital age. Astronomers use complex numbers to model the motion of celestial bodies and analyze signals from space. This approach allows them to make precise calculations and uncover the mysteries of the universe. Music theory and digital sound processing often rely on complex numbers to analyze and synthesize sounds. Fourier transforms, which break down sounds into their components, use complex numbers at their core. In advanced probability and statistics, complex numbers are used to solve certain types of integrals and analyze random processes. This mathematical tool expands the range of problems that can be tackled in these fields. Computer scientists use complex numbers in algorithms for graphics, simulations, and data analysis. Their unique properties make them valuable for solving a wide range of computational problems. Navigation systems sometimes use complex numbers to calculate positions and directions. This mathematical approach helps ensure accuracy and reliability in everything from GPS devices to autonomous vehicles. Weather models use complex numbers to simulate atmospheric processes and predict weather patterns. This helps meteorologists make more accurate forecasts and understand the dynamics of our planet's climate. Architects sometimes use complex numbers to design structures with unique shapes and properties. This mathematical approach allows for innovative designs and efficient calculations in structural engineering. Chemists use complex numbers to model molecular structures and reactions. This helps them understand how molecules interact and predict the outcomes of chemical processes. Medical researchers use complex numbers in imaging techniques like MRI and CT scans. These mathematical tools help create detailed images of the human body, aiding in diagnosis and treatment. Complex numbers are much more than just mathematical curiosities. They're powerful tools that have transformed science, engineering, art, and many other fields. By extending our understanding of numbers, they allow us to solve problems that were once thought impossible. Whether you're studying math, designing technology, or exploring the universe, complex numbers are there to help you unlock new possibilities.